Good morning, sir. Today I am going to explain design of circular wall under triangular water pressure with varying AST. These are the contents which I have covered in my PPT. First, introduction. Second, types of circular wall subjected to triangular loading. Third, design of circular wall. Fourth, an example. And fifth, references. First, introduction. Circular wall. It essentially consists of a base plate rested on the ground and a vertically erected shear wall. Types of circular wall are as follows: wall with fixed base and free top subjected to triangular loading, wall with hinge base and free top subjected to triangular loading, as well as trapezoidal loading, wall with shear applied at top as well as at base, and last one, the wall with moment applied at top. Since we are dealing with types of circular wall subjected to triangular loading, there are only two types, that is wall with fixed base and free top and wall with hinge base and free top. First, wall with fixed base and free top. In this, the wall built continues with their footing where the base is fixed and the top is free. The ring tensions at various heights are given in table number 9. The moment in circular wall are given in table number 10 and coefficient of shear are given in table number 11 respectively. Example, ground storage reservoir and water container are the prime examples. Then second, wall with hinge base and free top. In this, the base joint is continuous and the footing is prevented with smallest of rotation, where rotation is required to reduce the fixed base moment from definite value to say 0, which is much smaller than rotation that may occur. So when normal settlement takes place in subgrade, thus it may be difficult to predict the behavior of subgrade, and its base gives a safe design than fixed base. The ring tensions at various heights, which are free at top and hinge at base, are given in table number 12, and moment in circular wall are given in table number 13, and the coefficient of shear at base of circular wall is given in table number 11. Then the design of circular wall. The circular or cylindrical wall of a tank or a container should be designed for three different types of forces. They are as follows: design for tension, design for bending, design for shear. For design of tension, we use table number 9 from IS 3370 part 4. For design for bending, we use table number 10. And for design for shear, we use table number 11. This is the detailing given in given in IS 3370 part 2, clause number 8.1, especially for design for tension, which we are going to see in next slide. As you can see in figure A, if thickness is less than 200 mm, then we provide one-sided reinforcement. And if thickness is more than 200 mm, we provide alternate reinforcement as shown in figure number B. We have taken an example. Okay, first, design a GSR for the following data where the height of water is 3 meter, diameter is 15 mm. We have assumed thickness of wall equal to 150 mm, grade of concrete and steel are M25 and Fe415 respectively. First, we will calculate design constants. From IS 3370 part 2, table number 2 and table number 4, we get the value of sigma CBC and sigma SJ. Then we calculate design constants M, K, J and Q respectively. So we get the value M equal to 10.98, K equal to 0.42, J equal to 0.86 and capital Q equal to 1.53. Then we go for design of circular wall. First we will calculate h square by dt, where h is 3 meter, d is 15 meter and t is 0.15 meter. So we get the value 4. First we go for design for tension. As shown in table number 9, IS 3370 part 4, we get in coefficient value as 0.429. We calculate maximum hook tension from it, that is coefficient into W into H into R, where coefficient is 0.429, W is 10, height is 3 and R is 15 by 2. So we get maximum hook tension equal to 96.53 kilonewton. Then this is the table which I made for varying AST. It is made for each and every height given in IS 3370 part 4. Okay, first we will look at third column, that is h square by dt coefficient. Then from that we have calculated the hook tension respectively for each and every wall. Then we calculated AST, which is calculated by hook tension by sigma ST. Then we calculated minimum AST, which is 0.24% of cross section. Then we have provided a bar diameter of 8 mm each. Then spacing we have calculated. Last but not least, we have calculated AST provided. Then we go for check tensile stresses check. Tensile stress is equal to maximum hook tension upon AC plus M into AST, which should be less than 1.393 Newton per mm square. So I have prepared a chart AST for hook tension also. that for tensile stress also. So for each and every hoop tension at a particular height of the wall, we have calculated the tensile stress respectively, which is less than 1.3. That is, therefore, they are okay. Then we go for reinforcement needling. Since thickness is less than 150 with 200 mm, we have provided one-sided reinforcement. Then we go for design for bending. From part IS 3370, table number 10, we get interpolated coefficient equal to minus 0.0268. First, we will not prepare any chart as we prepared in design for tension for varying AST, because in bending we have to take the maximum value regardless. So we calculated maximum bending moment, that is coefficient in the W into H cube. We get bending moment equal to 5.43. From that, we will calculate the value of small d. We get 59.57. Then we provide a clear cover of 30 mm. We get capital D equal to 89.87 mm. From that, we will round up to the value of d in multiples of 25 mm. Since capital D is less than 1, since we have provided thickness of wall equal to 150 mm, so we provide capital D equal to 150 mm and small d becomes 120 mm. Then we calculated AST and then AST minimum. And we take the maximum of both, which I have got 404.74 mm square. Then we go for spacing and area provided by providing 8 mm dia. We got 100 mm center to center spacing. Then we provide area provided. We got 502.65 mm square. Then we go for bending stress check. Bending stress equal to maximum bending moment into y upon I, where bending moment is 5.43, y is d by 2, that is 150 by 2, and I is bd cube by 12, that is 1000 into 150 cube by 12. So we got bending stress equal to 1.45 Newton per mm square, which is less than 1.8 Newton per mm square, hence safe. And the bottom figure you can see is reinforcement detailing. Then we go for design for shear. From table number 11, IS 3370 part 4, by taking triangular load fixed base, we get an interpolated coefficient equal to 0.236 and shear force equal to interpolated coefficient into W into H square. So shear force equal to 15.93 kilonewton. Tau V equal to Vu upon Bd. And so we got tau V equal to 0.13. Then we go for percentage of steel. We 100 ASG by BD, we get 0.41%. By interpolating the value from IS 3370 part to table number 3, we get the value of tau C. We get 0.28 Newton per mm square. Since tau V is less than tau C, shear reinforcement is not required. Hence design is safe. Here our problem ends. Then these are the references which I have taken. First, IS 3370 part 2, and last IS 3370 part 4. Thank you so much, sir.